Hello, welcome to Chemistry Travels. We all would have performed experiments or chemical reactions in labs, such as our inorganic salt analysis or organic functional group analysis, where we just mix 2 or 3 reactants together and the reaction happens to form the product with a characteristic change, like it can be a change in a color or evolution of a gas, or sometimes it can also be evolution of a smell, a particular smell, or precipitate formation, and we identify the product to be formed. And certain reactions that we do in lab are really fast. You just have to mix 2 things together, 2 or 3 things together, and immediately you see a change. Like these reactions, if you react sodium sulfate with barium chloride, immediately sodium chloride and barium sulfate is formed, which is a white precipitate, right? So immediately you mix these 2 things together and you get the white precipitate of barium sulfate. And it's a very fast reaction. But at the same time, consider another reaction that we do very commonly, which is the test for aldehydes or ketones, the tolerance test that we do. Here we have the tolerance test, where we take the aldehyde or the ketone, we take the reactant and treat it with the tolerance reagent, and immediately do we get a reaction? Do we get a silver test mirror around our test tube immediately? No. You'll have to either keep it aside for some time, or you'll have to supply an external heat for the reaction to occur. Then only you get the silver mirror, right? So it's not a really fast reaction compared to the first one. This is a much slower reaction, right? And there are certain other reactions where maybe you'll have to give cold conditions, like you'll have to keep it in an ice bath or something. Like many coordination complex formations, you'll have to keep it in ice bath and all for the reactant to form, right? But if you look at some other reactions in our daily life, if you look around us, we see like the rusting of iron. We have the rusting of iron, which does not happen over a single day or few days. It happens over months or years, where iron slowly reacts with the oxygen present in the air and the water vapor in the atmosphere, leading to the formation of the rust, right? Fe2O3 protects H2O. It's a really slow process. Similar one is our fermentation process that we have here, right? Where we use this reaction for making wine and all. And you don't make wine over a day. It happens over so many months. You have to keep, like the sugar slowly is converted by yeast to ethanol and carbon dioxide, right? Fermentation process is also a really slow process. So what do we understand? Though all of these are chemical reactions, they all do not happen at the same speed. Some reactions happen in microseconds, while some would take few minutes or few hours for the product to be formed, and you might have to supply some external factors like heat or cold. And there can be other certain reactions that can take years or like so long to form the product. So we can understand that the rate at which the reaction occurs is different for different reactions. And it is chemical kinetics that studies this rate of the reaction. A rate of the reaction is studied by a branch of chemistry called chemical kinetics. And the chemical kinetics not only studies the rate of the reaction, it tries to understand the factors that affect the rate of the reaction. So the rate of the reaction would definitely be dependent on several factors, and in chemical kinetics we learn those things. Also, another thing that affects the rate of the reaction is its mechanism. So in kinetics we also study the mechanism of a reaction and study how the mechanism can actually affect the rate of the reaction. Okay, let's consider a reaction where reactant A is getting converted to product B. Okay, so if you need to know the rate of this reaction, rate is always a change in something with respect to something else, change in X with respect to change in Y. So in this reaction, what is it that changes in a chemical reaction? So we can say that the concentration changes for a reaction with respect to time. So you can represent the rate of this reaction in terms of concentration and time. For that, let's consider 2 times T1 and T2. So say at time T1, the concentration of the reactant A was A1, and at the same time T1, the concentration of the product B was B1. Definitely as the reaction proceeds, these concentrations would change, and at another time T2, you go further and you move to a time T2, and at that particular time, the concentration of A is A2 and the concentration of B is B2. So rate of the reaction can be expressed as rate of change in concentration of A or rate of concentration, change in concentration of B with respect to change in time, right? So the rate of the reaction can be written as rate of decrease in the concentration of the reactant, because the reactant concentration is decreasing. So the rate of the reaction is decrease in concentration of reactant, or it can also be an increase, rate of increase in the concentration of the product. Or you can also say that as the reaction proceeds, A is disappearing and B is appearing. So it can also be said that the rate of the chemical reaction A giving B is rate of disappearance of A or rate of appearance of B. Okay, now how do we write it? So rate is change in concentration by change in time. Now what is the change in concentration here for A? So we say that change by delta, delta A, change in concentration of A can be written as A2 minus A1. Change in concentration of B, delta concentration of B can be written as B2 minus B1. And next we need to know the change in time. So delta T equal to T2 minus T1, right? Now, how do I write the rate of the reaction? Is rate of disappearance of A or rate of decrease in concentration of A. So it can be delta concentration of A by delta T, right? Now we need, rate is always a positive quantity, right? Rate is a positive quantity. You can't have a negative rate. So you just multiply this with a -1, because delta A, A2 minus A1 is a negative quantity. This one is negative. A2 minus A1 is negative. So when I put that value here, this whole thing delta A by delta T will be negative. And to make it positive, I multiply this with a -1. Or in terms of B, if I write rate of increase in product concentration or rate of appearance of B, that is delta concentration of B with respect to time, so by delta T. And in this case, B2 minus B1, B2 is always greater than B1, so it's already a positive quantity, so this also would be positive, and unlike this case, you do not need to multiply with any minus sign. So this case is given as the rate of a reaction. We can write the rate of any reaction in this form. So let's look at this example. Hg and chlorine, mercury chlorine reacting to give HgCl2. So what is this rate of the reaction? So the rate of the reaction would definitely be delta concentration of Hg by delta T, and for reactants we have to put a minus sign also, or it can be minus concentration of chlorine by delta T, or in terms of product when I write it's a positive value, so it's delta concentration of HgCl2 by delta T. So this is how we write. Now consider the next example where hydrogen iodide Hi is dissociating to hydrogen and iodine. Now in this reaction we have 2 Hi. So how do we write the rate of the reaction? So rate of the reaction, we saw that it is minus delta concentration of reactant Hi by delta T, or it can be in terms of product, it is delta concentration of H2 by delta T, or concentration of the other product I2 by delta T. The difference is we have a 2 here in the reactant. So whenever we have a coefficient, some n moles or x moles are reacting, that will come as 1 by n. Right? I meant to say, if we have a reaction where Na gives Mb, this n and this m will come as reciprocals in the rate equation. Rate of the reaction we write. When we say rate, this would be for Na, it will be minus 1 by n delta concentration of A by delta T, and for the product I can say 1 by M because it has M moles. M moles of B are being formed, so the coefficient would go like 1 by M into the change in concentration of the product by change in time. Clear? Now, the rate that we spoke about was the average rate because it was a change in concentration over a selected period of time. We chose a T1, we chose a T2, and over the time from T1 to T2, what was the change in concentration? And that is the average rate of the reaction. But if you want to know the rate of the reaction at a particular instance or at a particular time, it is called the instantaneous rate. It is a change in concentration at a very particular time. So let's look at it graphically. This is a graph for a change in concentration of a reaction with respect to time, where A was giving B. So definitely concentration of A keeps decreasing with time and the concentration of B keeps increasing with time. Now if we consider only the A part or the reactant part, let's find out the average rate and the instantaneous rate from the graph. So we have the concentration of A versus time graph with the reactant concentration decreasing with time. And as we told earlier, at time T1 the concentration was A1 and at time T2 the concentration was A2. Now if I have to take the average rate, our average, we just do that A2 minus A1 by T2 minus T1. But if you want to know the rate at a particular instant, say at this point, what is the rate? So what you have to do is you need to draw a tangent, and the instantaneous rate is a slope of the tangent to the curve. It is a slope of the tangent to the curve, and the instantaneous rate is a derivative. So we can say that our instantaneous is definitely, this is for the reactant, so it's minus d concentration of A by dt, dA by dt. Or it is also the slope of that curve at that particular tangent we drew. So this is minus slope of that curve. So our instantaneous is negative of the slope for the reactant, and our average would be the difference in the concentrations by difference in time. Okay, as discussed earlier, chemical kinetics also studies the various factors that affect the rate of reaction. And certain factors that influence the rate of the reaction can be either the concentration of the reactants that we take, or if it's gases that we are considering, it is the pressure of those gases that we consider. And then there can be the temperature, like application of heat or cold can affect the rate of the reaction. And finally, the catalyst plays a role in affecting the rate of the reaction. And though catalyst is usually said to increase the rate of a reaction, there are certain catalysts that can also decrease the rate of the reaction. So a catalyst also influences the rate. And first we'll be looking into each of them separately. And firstly, how concentration affects the rate of the reaction, or how we can represent rate based on the concentration. And this representation of rate of the reaction in terms of concentration is called the rate law. It is commonly called as the rate law. Also, it is known as rate equation or rate expression. To write the rate law, if we consider a reaction where A moles of A reacts with B moles of B to give C moles of C and D moles of D as products. Okay, so we saw that the rate is proportional to the concentration, depends on the concentration of the reactants. So I can say that my rate of the reaction is proportional to the concentration of A and the concentration of B. So it's like concentration of A into concentration of B, and also there is a fraction, a factor raised to some power. A concentration of A raised to some power x and concentration of B raised to some power y. And this x and y may or may not be equal to this A and B. It's not always necessary that concentration of A has to be raised to A and concentration of B has to be raised to this number of moles B. Not necessary. It may or may not be equal. But it is some fractions A and x and y. It can be some numbers x and y. Okay. So rate is proportional. To remove the proportional symbol, we have to multiply it with the proportionality constant, and that constant is K, which is the rate constant, giving rise to the rate equation or the rate law or the rate expression we told. Rate equal to K, rate constant, into concentration of A raised to x into concentration of B raised to y, and this is our rate equation or rate law. Okay, and now this x and y are not theoretically obtained. You can't say what that x and y is looking at the equation. You need to do it experimentally. X and y are determined experimentally, giving rise, and finally we have this rate law, and we can say that this rate law is a mathematical expression where we write the rate of a particular reaction in terms of the products of molar concentrations of the reactants raised to a coefficient which may or may not be equal to their stoichiometric coefficients. Okay. And this x and y, as I told, they are experimentally obtained, and the sum of this coefficients, that is x plus y together, that is called the order of the reaction. We call that the order of the reaction. So together this x plus y can either be numbers like it can be 0, 1, 2, so on and so forth. It can also be even fractions, or like so 1 by 2, so we don't know. It can be anything. It can be fractions, it can be 0, or it can be whole numbers. And that is the order of the reaction. When we say, if I say it is 0, it means that K is like a power x into b power y. If x plus y equal to 0 means both of them has to be 0, x is 0, y is 0. So what can I say? It's like k into a power 0 into b power 0, right? So what to say? A power or any number power 0 is 1. So a power 0 is also 1, b power 0 is also 1. So I can simply say that in a zero order reaction, if I say x plus y 0 or the order of the reaction is 0, I am simply saying that the rate of the reaction equals to the rate constant, or it is independent of the concentrations of the reactants. Okay. So this was a rate equation where rate is k into a power x into b power y. And now let's find out the unit of k, or our rate constant's unit. For that, we write the units of those terms which we already know. First thing is rate. We know that rate is change in concentration by change in time. Therefore, its unit would definitely be unit of concentration by unit of time. That is, unit of concentration is mole per liter and unit of time is second. So the unit of rate would be mole liter inverse second inverse. And now K is the term that we need to find. We do not know what it is. Now A is a concentration, and we know that unit of concentration is mole per liter. So mole per liter, and there is a power x. B is also concentration, so it is also mole per liter raised to the power y. Now what do we say? That we know a mathematical form for powers. When we learn about powers, we learn that a power m into a power n equal to a power m plus n. This is a rule that we learned. Similar, this is of the similar form here. Mole liter inverse and mole liter inverse, they are the same terms and raised to two different powers. So I can write it commonly as mole liter inverse and sum of the powers x plus y. I can write it in this form. So mole liter inverse second inverse becomes equal to k into, commonly I write mole liter inverse raised to the power x plus y based on this mathematical formula in powers. Now I slightly rearrange to bring k on the left and all the other known terms on the right. So it becomes mole liter inverse second inverse by mole liter inverse x plus y. Now we know that x plus y is the order of the reaction. So this x plus y can be together written as a term n, which is the order. So I'm putting it as n, and then again if you look, you will see that it's of the form a power m by a power n. So mathematically a power m by a power n equal to a power m minus n. So you have to, the common power and the common term has to be written as such. Here mole liter inverse is the common one which is there in the numerator, and as well as mole liter minus 1 is there in the denominator also. So we write that commonly, and then the powers we just subtract them, m minus n. So if you do that, finally you will get the rate constant k to have a unit of mole 1 minus n second inverse liter n minus 1. This is going to be the unit of the rate constant, and where n is the order of the reaction. It was x plus y which we took as n, and we already saw that in the rate equation of the rate law, x plus y is the order of the reaction. So let's just see for if n equal to 0. So if I consider n equal to 0, It's a zero order reaction. So for zero order reaction, this the unit of rate constant would come out as mole 1 minus n. So 1 minus 0, that's 1. Second inverse liter n minus 1. So liter 0 minus 1, that's minus 1. So mole second inverse liter inverse is a unit of rate constant for zero order. And if I consider first order, mole 1 minus n, n is 1. So 1 minus 1, that's 0. So mole is 0. Then there is mole power 0. So anything power 0 is just 1. Okay, so we did not write that. Then there is second inverse and liter raised to n power minus 1. n is 1. So liter raised to 1 minus 1, that is liter raised to 0. Anything raised to 0 is just 1. So we are not writing that. So the unit of rate constant for first order is second inverse. Now if I consider the second order reaction, n becomes 2. So in that case, mole becomes mole power 1 minus n, that is 1 minus 2, that's minus 1. Second inverse, liter n minus 1, 2 minus 1, that's 1. So mole inverse, second inverse liter is a unit of rate constant for second order reaction, and you can write this for all orders. Okay. Another term similar to the order of the reaction is the molecularity of the reaction. And molecularity refers to the number of reacting species in an elementary reaction that collide simultaneously to form the product. So molecules come and collide together to form the product, and number of such reacting species that collide with each other simultaneously in an elementary reaction to form the product give rise to their molecularity. And order, when we considered, it could be 0, it could be whole numbers like 1, 2, 3, or it could even be fractions. But molecularity can never be 0 or fractions, it is only whole numbers like 1, 2, or 3. And order was obtained experimentally. You can't look at an equation or theoretically you can't predict the order of a reaction. However, molecularity can be predicted theoretically. So if you consider these examples, your dinitrogen pentoxide is getting converted to dinitrogen tetroxide with the liberation of oxygen, and this is a unimolecular reaction. But if you consider HI decomposition to hydrogen and iodine, it is a bimolecular reaction where two molecules of HI has to come together, collide with each other to form the particular products. And finally, we have an NO and O2 reacting together to form nitrogen dioxide, and this is an example for a trimolecular reaction where its molecularity is 3, because 3 moles have to collide with each other together to form the NO2 as product. Okay, and also the molecularity cannot be more than 3. 3 itself is less popular. Mostly reactions are either unimolecular or bimolecular, because more than 3 molecules colliding with each other simultaneously to form product is practically, the probability is very less, it's almost impossible. So usually molecularity is either 1 or 2. Reactions are unimolecular or bimolecular. As we discussed the order and molecularity of reactions, a set of reactions that come as exceptions are the pseudo-first-order reactions. Now they are bimolecular higher order reactions, but though they are higher order, they behave as first order. For example, we have this reaction where we have the hydrolysis of this ester to acid and alcohol, where we have the ethyl acetate ester that getting in presence of hydrolyzed, it is being hydrolyzed with water. And the quantity of the second reactant, generally this is a second order reaction, we can say, where the rate would depend on the concentration of ethyl acetate as well as the concentration of water. But in this case, what happens is this concentration of water is too high that the change in concentration is almost negligible. Since the concentration is too high, the change in concentration is too negligible to be considered for affecting the rate. So we say that the rate is dependent only on a considerable change is observed only in case of the concentration of this. So the rate is dependent only on the concentration of one of the reactants, and this is how the rate is written, and it happens to be first order, where this K that we have is actually K dash into concentration of H2O, and that concentration of H2 is also considered, since it's too high value, the change is negligible, so that is also considered as a constant, and the K we have here is actually K dash into H2O, which is a constant, into the change in concentration is only for ethyl acetate, and that's written here. Another example is the inversion of cane sugar, where cane sugar again with excess amount of water. Water is too high here also, so change in concentration of water is negligible. So we can write the rate of the reaction only in terms of cane sugar's concentration, that is R equal to K into C12H22 O11's concentration, where K is similarly K dash into H2 in this case also. Okay, so that was the first part of chemical kinetics, and we'll be looking into the remaining topics in chemical kinetics in the upcoming videos. Thank you so much.